Hey, welcome back. This lecture is going to be a shorter one because the priority queues lecture was, pretty much a lecture and a half. This lecture is going to be dealing with the introduction to disjoint sets. We're going to talk about the abstract data type today, and then what we'll be doing in the next two lectures is talking about the basic implementation and the more advanced optimized implementation of disjoint sets. So to begin with, we have to talk about what disjoint sets are. And what we're basically referring to here is the idea of we have some universe of elements, which we can call, U, like that. And what we're basically saying is we have some collection of sets, S1, S2, S3, and so on, up through Sn. Some collection of, n sets in this universe. And typically, that's something that we've dealt with before. In general, just you have some collection of elements, and you maybe have, these particular 3 elements in some set, or those 5 elements in some set, or whatever. But what's unique about this particular setup is there's 2 properties that are going to be true. And the first one is that if we take the union of all of the sets together, that it's going to be equal to the universe. Or in other words, every element is in at least one set. So all the particular sets that we're dealing with, there's no way to say, well, we have a set of integers, for example, and the number 2 doesn't happen to be in any of our sets. That's every element's going to be in one set. So if you combine all the sets together, you get the entire collection of elements. The other property is going to be one in which we say that for any I and j, for all I and j such that I is not equal to j, so for every 2 unique pair of unique subscripts, we'll say that the intersection of Si and Sj is equal to the empty set. So, of course, if I is equal to j, then we're just doing a set intersected with itself, and that's the original set. But if we say we're definitely dealing with 2 different, so that when Charles scans it in, that shows it very clearly. We're definitely dealing here with 2 different sets, and for every pair of 2 different sets, their intersection is non-existent. There are no elements in common. Or in other words, no element is in more than one set. And so, of course, if every element is in at least one set, but no element is in more than one set, what that gives us is that every element is in exactly one set. And that's the idea behind disjoint sets here. We're saying, given the universe of elements, what we have here is some collection where we say that we've managed to divide the universe up into a particular number of sets. And every single element is in one set, but no more than that. So you can almost just think of partitioning all your elements into a collection so that that's the case. Now, one example of this that we're going to be dealing with pretty heavily is, or not, I shouldn't say that. One example that will come into play in what we'll be dealing with very heavily is the modulus operator. Think of if we talk about equivalence mod 6. And we can say, well, we have everything here that's equivalent to 0 mod 6, everything that's equivalent to 1 mod 6, to 2 mod 6, to 3, to 4, and to 5. And so if we have if we've divided our elements up in that way, well, those are disjoint sets. There's no single element, no integer you can name, for example, if this is a collection of integers, which we would be assuming we have if we're doing modulus. There's no integer that exists that's both 0 mod 6 and 1 mod 6. It's one or the other. And so there's no integer that could be a member of both sets, and yet every single integer is going to be one of those 6 numbers mod 6. You divide it by 6, the remainder is going to be 0, 1, 2, 3, 4, or 5, one of those 6 values. So every integer would have to be in one of those collections, but no integer could be in 2 or more. And so that's one example of, if we're going to say take a collection of integers and divide it up based on equivalence to mod 6, or equivalence modulo 6, then we get a collection of disjoint sets. That's one example. Another example might be, in real life you have computers, and you have consider all the computers in the world. Now, which computers can have email sent back and forth between them? And now, assuming that every connection is between two computers is two-way, and that any two, if one computer can contact a second, then that second one can contact a first, then you can think of the individual networks as being disjoint sets, where we can say here, if A can contact B and B can contact C, then A can contact C. And so this is going to come into, what this is going to be important in doing is modeling equivalence relations. And we've seen two examples of equivalence relations right here. More specifically, and this gets into a little bit of discrete math, and I'm not sure for the remote folks how many of you have had discrete math or discrete math course, but it is a prerequisite for 225. I'm going to quickly do what I do in the main lecture too, which is to just remind everyone what an equivalence relation is. In general here, when we talk about a binary relation, we're simply talking about some formula or some description on two values where the result is true or false. And so we're saying here, well, I've got, if I say A is related to B, or I can say A is not related to B, but we're basically asking, given these two values, are they related or not? And one example of a binary relation would be less than, where we say, given two integers or given two any values of whatever we're dealing with, those two, either the first is less than the second or it's not. And so this expression is either true or false. And an equivalence relation is this kind of idea, this kind of where we say, are these two elements related through that relation or not? Is this relation true or not? And there's three particular properties that an equivalence relation has. First, it's reflexive, which says, for all A is related to itself. And so that's certainly not a reflexive relation because A is not less than A. And so less than would not be reflexive, but if you have less than or equal to, that would be reflexive because every number is less than or equal to itself, but no number is strictly less than itself. And so this would be reflexive, but that wouldn't. Likewise, you have a second property, which is it has to be symmetric. And again, the way we would notate this mathematically is for all A and B, if A is related to B, then that implies B is related to A and vice versa. So that's what that means is if this, for any two elements in your universe, if that's true, that has to be true, and if that's true, that has to be true. And you notice that the less than or equal to is not symmetric, because while it's possible for A to be less than or equal to B, and yet B is not less than or equal to A. If that was 2 and that was 5, 5 is less than or equal to 2. 2 is less than or equal to 5. That does not imply that 5 is less than or equal to 2. And so that would be, even though it's reflexive, it's not symmetric. And then it also has to be transitive, which says for all A, B, and C, if A is related to B and B is related to C, then that implies that A has to be related to C. And certainly that would be transitive if you say, well, 2 is less than or equal to 5 and 5 is less than or equal to 8. Both of those are true, and that would imply that 2 has to be less than or equal to 8, which of course we know is true. But even if we somehow didn't, what we're saying is, well, if those two are true, if 2 is less than 5 and 5 is less than 8, then it goes without saying that then that 2 has to be less than 8 as well, if this is a transitive relationship. So that's all. The math description is here, but these are just some tangible examples to give you a feel of what we're talking about here. And if we go back to something like the modulus operator, well, certainly that's going to be an equivalence relation. If we say, our relation here is that A is equivalent to B mod 6. And I'm not going to go ahead and do some sort of formal abstract algebra proof of any of this, but just to kind of illustrate quick examples, certainly 17 is equivalent to 17 mod 6. Any number, in fact, would be. 17 mod 6 equals 17 mod 6. Likewise, if we say 11 is equivalent to 17 mod 6, then that's going to imply that 17 is equivalent to 11 mod 6. We don't really, what we're saying is the order in which we list the numbers makes no difference. So if 17 mod 6 equals 11 mod 6, then 11 mod 6 equals 17 mod 6, and vice versa. And that seems like, well, maybe it's common sense. But the point is that we're saying this is symmetric. The order in which things are listed doesn't matter. And then transitive would, an example would be saying if 11 is equivalent to 17 mod 6, which is the case, and if 17 is equivalent to 29 mod 6, which is also the case, then that means that 11 has to be equivalent to 29 if we're talking about mod 6. Both equal to 5 mod 6. So there's an example of how the modulus, again, I haven't done any formal proof, but just to kind of illustrate with real numbers, that the mod 6, equivalence mod 6 relation is an equivalence relation. It's a relation first and foremost because two numbers are either equivalent in mod 6 or they're not, but then it satisfies the properties, the three properties needed to be an equivalence relation. And these are rather important to us because we have situations just like that, the one I described earlier with computers, where we say, let's say I have here a, again, deal with the idea of if we have sort of a two-way communication channel between two computers, and I have another two-way communication channel between two more computers, then if I'm able to freely pass messages across any one of these channels, then that would be an equivalence relation, because any computer can certainly contact itself. It's already got all its information right there in the memory in the hard drive. And if A can contact B, B can contact A, because we've said these are two-way channels. And if I can pass a message from A to B and also from B to C, then that means A can talk to C by passing messages through B, which is kind of how things work with routers and such. And so all we're saying here is because these two are connected through this two-way channel and these two are connected through this two-way channel, that means if A wants to contact C, it does have the ability to do so. So that means A and C are essentially contacted through a two-way channel, not directly, but they can be in touch through B. And so this idea of a two-way communication channel between two computers can be thought of as an equivalence relation. Whether they're directly connected or not isn't what's important. The point is, do we have a communications channel? And that works in both directions. And that idea is an equivalence relation, that relation. Are two computers connected in that fashion or not? And so that those kind of things can be important to us. In fact, what we might want to do is consider having a listing here, a list of all connected, not directly connected, but able to communicate back and forth with each other pairs. So I might say here, well, A is indeed related to B, and B is indeed related to C, and therefore I can have A and C communicate, so A and C would be connected as well. And that might be something we want to keep track of is which particular pairs of elements in a universe are related. And the disjoint set structure is going to very nicely model equivalence relations because basically an equivalence relation will break a collection of elements into disjoint sets. And you can go back and think about the modulus concept that we wrote up earlier. Modulus equivalence mod 6 was an equivalence relation, and it broke the set of all integers into disjoint sets. And I'm not going to prove that either, but that will always be the case for equivalence relations. If you take an equivalence relation and you apply it to the universe of elements, that universe will be broken up into disjoint sets, which are called equivalence classes, but that's not a term you need to remember unless you happen to remember it from a discrete math course. But another alternative name for them will be equivalence classes, and our disjoint sets are going to model those equivalence classes. We'll have a set for everything that's connected as equivalent to 0 mod 6, and a set for everything that's equivalent to 1 mod 6, and a set for everything equivalent to 2 mod 6, and so on. So our goal is to model those kind of relations, to have disjoint sets. And the reason for doing so is because the idea of storing individual relations is going to be something that we're going to talk about in a second, tends not to be as nice as simply storing the sets. So what we will eventually get to is, instead of storing a bunch of individual relations and saying, if I want to know if two values are related or not, I simply try and find their particular pair. What I'll do instead is say, if I want to know whether two values are related or not, I will simply determine if they're in the same set. And if two values are indeed in the same set, then they must be related. And if they're in different sets, then they must not be related. And that's going to tend to be easier, as we'll see, than trying to keep track of saying, well, 0 is related to 6, and 6 is related to 12, and 0 is related to 12, and 12 is related to 18, and 6 is related to 18, and 0 is related to 18, and having to store all these possible relations. If you have n elements in your universe, you have n squared pairs. If you're going to be able to let an element be paired with itself, 0 is related to 0, of course. So if you have n elements in the universe, you have n squared pairs, and having to search through a database of size n squared would be a pain. And so it'll be easier to deal with things in terms of storing things by disjoint set. And then when you want to know whether two elements are related, you will simply look up both elements and say if they're in the same set, they're related. If otherwise, they're not. And the question that comes into play is, what if we insert a new relation? What if we have a computer D here? And we say now, I'm going to have a connection to one of these two-way connections from C to D. Before D was by itself, we could say A was related to B, B was related to C, and therefore A was related to C. And of course, we'd have to have the reverse as well, that B is related to A, and C is related to B, and C is related to A, and list all those. And now suddenly C gets connected to D, and the question is, can we do that? And the answer is, well, we can, kind of. What we have to do is have a bunch of side effects as well. If I connect D to this network, D is not just connected to C, it's connected to B and A as well. And more generally, we could sort of write this out. This will sort of be a more abstract form. But let's say we can say the A, B, and C, and D, E, and F are 6 computers. So I have here, let me write up here. This is one connected network, A, B, and C. And I can say that A can speak to itself, and to B, and to C. And B is connected to A and itself and computer C. And C is connected to computer A and B and itself. So we've got that situation there where you've got now a collection of 3 computers, and so those are all the different ways and they're related to each other. You can have any 2 of those, pick any 2 of those 3 computers in any order, and they're related to each other. Or actually, just say pick a computer from that collection, pick another computer from that collection, which could be the same one, and they're related. And your real-world analogy of that is take 3 computers and connect them, and of course, every one of them can get every other computer's data or whatever. And then maybe we've got another collection here, a completely different network, not connected to the first one, with 3 more computers. So we say, well, also, so D is related to D, and also E and F, because it can communicate. Certainly, E can communicate with D, E can read its own data, and E can communicate with F. And then F can communicate with F, and I missed D here. So F can access D. So we've got now, out of the 36 possible relations we could have listed for 6 elements, we've got 18 of them. A, B, and C are all connected to each other. D, E, and F are all connected to each other. And this now, and the other 18 relations are not true. C is not connected to F, and C is not connected to E, and so on. And so this would be what we'd have to do if our attempt to learn whether 2 elements are related or not involved listing all the relations and searching through them, which we said we're not going to do, and here's why. We've got 18 possible relations for 6 elements. And now, if you were to inspect all these different relation listings, we could certainly say that all the equivalence rules work. Pick any 2 values in your universe. If your universe is 6 elements, A, B, C, D, and F. Pick a value, pick another value, same or different. And if they're the same, they'll always be, the relation will be here. A is related to A, B is related to B, C is related to C, F is related to F, E is related to E, D is related to D. So it's transitive. It's also symmetric because for any pair you've got, you'll have its reverse somewhere in the list as well. And it's also transitive. Just to show you an example, A is related to C is related to B, and therefore A related to B must be somewhere in here, and indeed it is. It's right there. So our collection of relations here is transitive, symmetric, and reflexive. So now what we're going to do is insert this relation. A is related to D. So we'll connect the computers A and D. And we want this to continue to be an equivalence relation. So firstly, we can't, if we're continuing to have an equivalence relation, we're saying we're connecting them with a two-way channel of some kind. And so that means that we can't really insert A related to D without saying, well, D is related to A as well. Yes, A can talk to computer D, but D can also talk to computer A. And in addition, if we've got this two-way channel going around, then that means that everything that A could talk to can talk to D and vice versa. So we're saying here, we've got, here's A, B, and C, here's D, E, and F, and now this is one network that I'm connecting, and this is another network that I'm connecting when I connect A and D. And I say, well, not only can A talk to D and vice versa, but now everything that A could talk to can send messages through A to D. Everything D can talk to can send messages through D to A. And everything that A can talk to can send messages through A and through D to everything that D can talk to and vice versa. Or essentially, we're saying things like, well, if it's true that A is related to D, and it's true that D is related to E, then that would imply that A is related to D. And that would have to be added to your collection as well. So if you want this to continue to be an equivalence relation, you can't just add one pair. Because adding that one pair implies a bunch of other things have to be true as well. It implies, if we're only dealing with two-way connections, if you're saying, well, now A and D are connected by a two-way connection, well, you're also saying D and A are therefore connected by a two-way connection as well. And then we're also saying, well, if that's the case, then B and D can talk through A. Or here what we're saying is A and E can talk because now A can pass a message to D, which can forward it on to E. And therefore, that would have to be added to the collection. And in fact, A related to any of these would have to be added. All of these are related to A. All of these are related to D. D is related to all of these. And all of these are related to all of these. And all of these are related to all of these. Essentially, what we're doing is now everything is related to everything else. Because of the fact that we have an equivalence relation here, when I add another two-way connection between stuff in this network and stuff in this network, now everything's connected to everything else. Because of the side effects that occur, when you're dealing with equivalence relations, you can't add just one relation, because then it won't be an equivalence relation anymore. We're changing what the particular relation is by saying, well, now we have a different set of facts that are true and false. But what we're doing now is we're saying, well, by virtue of adding this relation, I now, in order to keep it an equivalence relation, need to add a bunch of other stuff as well. You can't insert just one relation necessarily. What you are essentially doing is finding the union of two sets. If I want to now make an element from one set related and an element from a completely different set, if I want to make those two related, what I'm essentially going to be doing is also making everything else in A's set related to everything else in D's set and vice versa. When we're talking about equivalence relations, what the whole point of this is that adding a relation is the equivalent of finding the union of the two sets that those elements are a part of. You can't add the one relation and not add everything else like A, R, E that go along with it. And here's your real-world example. If you're going to connect computers A and D, well, now suddenly it connects a whole bunch of computers to a whole bunch of other computers. There's a side effect that happens naturally when you're dealing with equivalence relations. And so, if you're going to be worrying about having a collection of all true pairs, if you want to know whether two elements are related, you need to search down that collection of all true pairs, which can take a while. And if you want to insert a new relation, which you know is going to result in a bunch of other new relations being inserted, new relation pairs being inserted as well, then what's going to happen here is you're going to have to basically search through all of these collections over and over again, finding all the transitive relationships, finding all the symmetries that arise from that, and so on. It'll be a huge pain. And so, as if searching the entire collection to find one particular pair wasn't bad enough, now inserting a new pair is going to now result in a bunch of other pairs like DRA and ARE being inserted. And that means we're going to have to pass through this collection over and over again with some algorithm trying to find all the pairs that should be added. And that's not going to be an appealing solution. So we could represent this idea. If our goal is to say two elements are related or not, so I know, for example, can these two computers talk or not? If our goal is to answer questions like that, we could keep track of all the pairs that can communicate, but searching that list could take a while, and more importantly, inserting a new connection is going to require, traversing that list in a number of complicated ways, trying to find all the other connections that result from that. And it's going to be unelegant and time-consuming. And the way we'll deal with things instead is to simply say, well, I'll have the set ABC, and let's call this set 1, and we'll have the set DEF, and we'll call this set 2. And then if I want to, if it becomes the case that now A is related to D, the result of that is going to be a union of set 1 and set 2 to produce this new set. So inserting a relation is the equivalent of creating a new set. And then if I want to know, this is what I'm inserting. And if I want to know are A and D related, what I will do is basically do a find on A, return, let's say we call this set 3. The find operation returns name of set A is in. And then I can do a find on D and do the same thing, but for D, return the name of the set D is in, and then compare the two names. In the top case, if I do a lookup on A, I get 1. If I do a find on D, I get 2. So if I do a find on both elements, I get two different set names, 1 and 2, and therefore A and D are not in the same set, and therefore they're not related. Where once I've done a union on the two sets, then when I do a find on A and D, I get 3 in both cases, and so they're in the same set, and so they are related. And so that's how we're going to approach this. Rather than having a huge bunch of true pairs, we'll simply say, let's just build sets instead. And we'll have the idea here of saying, well, all the elements that are related to each other will be in one set. And so if two elements are in the same set, then they're going to be then we know they're related, and if two elements are in different sets, we know they're not related. And to add a new relation to the collection, along with all the side effects that will generate, what we know then is adding a relation between two elements in two different sets basically is saying all the relations that get joined or that get created as a result of that, what we basically are doing is saying all these elements now from the two sets to belong in one set. So it's a union of two sets. Just like if you take two computer networks and you say everything in this network is completely connected to each other and everything in this network is completely connected to each other, once you put that two-way connection between them, now you've got essentially one large network where everything is completely connected to the other. So that's the idea, merging two disjoint sets with being modeled as equivalence relation. If you want to add a connection between the two sets, you're really taking a union of the two sets, and everything's related to everything else. And so disjoint set structure, sometimes called the union find structure, because the only two operations we're really concerned with are union and find. The find operation here helps us determine if the relation we are looking for is true or not. And the union is the equivalent of our insert. And there is no equivalent for a remove if we want to remove a relation. And the reason being, if this is our set, and we want to remove the relation A related to D. Well, keep in mind, if I have this and this, if A is related to E and E is related to D, the two of them together imply that this has to be true. So if I want to get rid of that relation, I have to get rid of one of these two as well. Because if both of these are true and yet that one's not in the collection, then we don't have an equivalence relation anymore. And so because of transitivity, if that's going to be gone, then one of these has to be gone as well. Otherwise, we'd have both of those and not that, and then it's not transitive, and therefore it's not an equivalence relation. So essentially what we're saying is, what we want, it's not enough just to say, well, A is no longer related to D. A and D need to be in completely different sets. And these kind of side effects that generate, okay, we lose other relations as well, as a result of dividing A and D into different sets. And there are different ways we can do this. So we might say, let's pull A off into its own set. Now clearly the relation that's been severed is, not only have we severed those two, but we've gotten rid of that one. A is no longer related to E. We could have also done things this way. Now again, A is not related to D and it's not related to E. We could have also pulled D off by itself, B, C, A, E, and F. Now we've kept this relation, but we've gotten rid of this one, of course, and that one as well. But there's no way to arrange these values so that that is not true, but those two are both true. That won't be possible. The question, though, is how do you want to divide this up? If I want to remove this relation, if I say I want to somehow, if I want to say A is related to D, well, I can just connect any two elements in an A set and D set, and they'll become connected. If I want to say now, given this large computer network, I want A to not be related to D anymore, how do I do that? Of course, the physical layout says you just break that link. But in general, if we have a bunch of things that are connected and I say A is no longer related to D, the question is, how can I break that relationship? And these are three different ways we can break that relationship. And what we're saying is they're all going to have other side effects as well. We've broken other relations besides just A and D being related. Other things are no longer true as well, including one of these now must become false. And that's the idea here is that remove is not well defined. If I want to get rid of a particular pair, just as with insert, when I insert a pair, I need to insert other pairs as well to make it still be an equivalence relation. Likewise, when I remove one pair, I'm going to need to remove other pairs as well, like one of those two, to make it still be an equivalence relation. But there's no clearly defined way to do that. We have at least three options here, and you can list a few more as well. And so rather than trying to come up with some definition, we just recognize that, okay, there's a number of ways I might get rid of this particular relation. There's a number of other ways I might break these two sets up to make sure that A and D are not related. Since there's a number of different ways of doing that, we're not going to have a standard definition for remove, and we won't deal with it. Insert, there's only one thing to do. When I want to make two of these related, I merge their sets. But breaking up the set, there's a number of ways to do it. There's only one way to union two sets. So the point is remove, the concept of removing a relation and all of its side effects is not well defined because there are a number of different types of side effects we could pick based on, you know, what division of sets should we have, and that's what we see here. We're given a choice. Well, one of those two has to go, or both of them, but we can't keep them both. And so we have a number of different side effects that we might have in addition to removing that one. And so since remove is not well defined, there's not a clear, definite one way to do remove, we're not going to have it as part of the standard structure. And so all we will really have is union and find. And so we will talk next time about how to go about making that work. You know, when we have a union, when we have a collection of elements, how can we implement the idea of given two sets, merge them into one set, given an element, return what set it's in. Those are the two operations we're going to be after with disjoint sets, and we've kind of tried to explain why those two operations are meaningful to us. And what we will do next time is look at possible implementations and come up with the one that works the best. And that's it. See you next time.